For those of you who are returning to the Climate Change Seminar Series, thanks for coming back. Those of you here for the first time, welcome. In fact, how many first-timers do we have here today? We've got several more coming up on site. I guess we'll just get started here. I want to introduce Dr. Rick Snyder from the University of California, Davis, and he'll be speaking about climate change impact on agriculture.
Okay. Thank you for inviting me. I'm Rick Snyder. I don't know how many people know me here, but I'm the biometeorology specialist at Cooperative Extension for the University of California, and I work out of Davis. My background is I work a lot on evapotranspiration and engineering, so I work a lot with the California Department of Water Resources, a lot of work with loss protection, type information. When I was preparing this presentation, I was trying to think, how do I do this? Because there's 230 crops in California, and all of them are going to be impacted by climate change. So I had to narrow it down a bit. I could make it very technical, or I could make it very simple, and I played around with it a bit. So what I decided to do is give you a couple of examples. It's difficult to say exactly what will happen with climate change because it hasn't happened when we've been here in the past. Because when you talk about climate change, you're talking about thousands of years. But I can't talk about weather change, because we have some weather records that impact that kind of agriculture in California. And think about it, we can make some implications as far as what climate change might do. I'm not going to say a lot about climate change because all of my previous speakers talked about it. This is a slide that shows the California daily temperature change. California EPA report from the governor. You can see that there's a big range of what different models say as far as how much temperature might increase. Difficult to say which one of those models is correct. Difficult to say if something might change over time, and maybe these models won't work out in the end, or maybe they're underestimating, overestimating. So for sure, this is the best guess of what might happen, range of what we might expect. Well, most people talk about global warming. They talk about temperature. A lot of times they ignore other things like the wind, and humidity, and other factors, which are really important for agriculture. A lot of our work in cooperative extension has to do with pest management. It is a big factor. I work a lot on frost protection, which is a big problem in California. We're talking about global warming all the time. I don't know how many of you realize that southern Yuba County last Sunday, there's a lot of major crops in the area because of frost. So it's still a problem. Not only the increase in temperature, but it's also how variable climate changes that affect all kinds of things. So I'll talk about what are the possible climate change impacts on agriculture. Well, we could have more droughts, we could have more floods, all kinds of things happen. There are possibilities we could have water and heat stress. Major droughts that cause water stress in crops. Most of the crops in California are irrigated, so we can on water supply. But crops are not. About get really high temperatures, you can have best effects on plants. Those are things that we need to do as well. Climate change can have effects on phenology and growth. Phenology we're talking about when you reach growth stage, affected by temperature. Growth is affected by temperature, but it's also affected by fertility, it's affected by water availability, and other factors that affect growth. So it's not only fill requirements could be affected if we're having global warming, if that has a regional effect. Filling is we might have problems with room in a lot of the crops. Pollination is something so we don't get a good crop set. Pollination again is a big problem. The almond growers have a lot of trouble if they get rain during pollination. It's a problem for almond growers. This is an example. You can also have other crops of pollination be affected because they're at different rates. Sometimes they help with pollination. They don't come at the right time. And so there's a lot of factors that affect that. Frost, dew, and fog all can be affected by climate change. One thing that I still remember when I was a student, my professor talking about climate, and he said the one thing that I know for sure is fairly predictable the last 100 years, and it's a lot more variable in the past, but I expect it to happen regardless of whether humans are affected or not. It probably is very predictable. We have more frost like we did last summer. Dew has a big effect on users. I don't know how many of you have lived here for a while, but I think fog is changing. We don't get as much fog as we just in the last 10 years. That has a big impact on culture. They wouldn't be growing citrus in the San Joaquin Valley. Pests, huge effects of climate change on pests. Some of them are better, and some of them are worse. Our climate change may make some of them work. So there's a lot of different. And you could end up with lower yield, or you could end up with higher yield, depending on what it is. In some cases, you're on the cold edge, if you warm it up a little bit, you're food production. I expect that over time, depending on how quickly it will happen, there are a lot of microplastics. I came to California, I remember the first thing I thought of, oh, what a place in the world. So there's huge difference one side of the valley to the other. It's probably bigger than. Okay, so climate change effects on agriculture. Well, these are some questions that I came up with. Well, the first one is the climate warming? And I would say yes. The evidence for global warming is pretty strong. The impact of that on a regional climate, I don't know for sure. A lot of people studying, trying to downscale from global climate models down to regional climate models. There's a range of global climate models, and there's a range of regional climate. So which one we pick is still a bit of a question. But the evidence for global warming is pretty strong. I don't think anybody questions that anymore. What will be the effect on agriculture? Well, nobody really knows because we don't know exactly what's going to happen. I do know that things will change. Crops will move around. We may have different pest problems than we have in the past. Nobody can really predict what's going to happen. Try to make some guesses at it. Try to come up with ways that we can adjust for it when it happens. Growers really need to worry? Well, maybe. Things are going to change for sure. So they have to adapt. Maybe they have to change their pest management practices, or again, they may have to change varieties. They haven't had to do in the past. Can we predict what will happen? Well, can we forecast the weather next week? I always find that a little bit questionable. I think we're pretty good at forecasting the weather. That gets more and more difficult to actually predict what will happen. You can't predict the weather next week. It's really hard to predict what climate change is. So this is a difficult problem. There could be other things that can happen. Everything. So we need to be prepared for everything. Have some plans in the works that we can adjust, and we do have plans. Well, I'm going to give you an example from Napa Valley. I was asked by the wine growers up in Napa Valley to give them a talk on climate change. And so I'm going to give this as an example because it kind of gives you an idea of what's important for. The reason why they asked me was, first thing was they heard a report from a scientist guy who wrote a paper from Southern Oregon University. He said the wine industry was going to move to Oregon. So immediately all the wine growers in Napa Valley were worried. Of course, he's from Southern Oregon. Oregon. That's why they asked me to come there and talk. They were worried about whether or not. One of the things that the wine growers are doing, they have things after the season. They like to do wine. The longer they leave it there, the more likely they are to hot, dry winds and have that desiccation. Really concerned about themselves and lost water. Okay, well, the question is, how often is this going to occur? So that's what they really know. What's the risk if they leave those berries hanging on the plants longer? What's the risk if they don't get a hot, dry wind? That's the thing they all go. What's the risk if they're going to have lost it? What's the risk if they're going to have important food? What's the probability of risk? That's, and there's also floods, drought, farmer needs to know how often. As a rule of thumb, when I talk to farmers about crops and about crops, I figure you're probably going to lose your crop. That's pretty common, depending on where you are. Some places they don't have very much. I came to California. I came from Iowa. I can still remember the first phone call I got. Was called me because he was putting a winery in a vineyard down in my Modesto. Good location. First question I had asked him, where's Modesto? I had no idea where Modesto was. And, but you know, I talked to the farm advisor down there. That's now. And it was interesting because then he was telling me later that Gallo has very few problems. Second call I got was, you guys are pretty sophisticated. They told us wine growers are not very successful. So anyway, when I went up to talk to them, I thought, oh, I don't have a lot of time. Talking about climate change, talking about change. I don't have that. I don't have that data. That's up to time. But I do have the last. I said, okay, well, I can talk to you about what's happening with others. You can make your own idea. You have the weather data. So that's what I'm talking about. This is an example. This is showing the April mean temperature. I also had to adjust this down to the valley. So I had correlation between this data and data down. You don't have data right back. The upper line there, the red line, is showing the trend. One. Pretty clear that both of them are going up. Maximum temperature is going up. Minimum was going up faster. This was in not the last IPCC. One before that was one of the points they made. Last one, they didn't say that. Because all the data I look at in California makes sense. Another one, this is showing the alignment. Here again, twice. Again, if you look at other locations, and this is showing the September mean. This is the period when they're worried about harvest. Here again, one thing I forgot to mention, look at how variable the maximum temperatures are in the fall. It's summer. quite animated and I move around a lot. It's hard for me to stand in one place. I did 2 sabbaticals in Italy, and I'd like to not talk about that too. Catching, it's like a disease. But anyway, one of the things is that it's much less variable in the summer than it is in the spring and the fall. So I was trying to emphasize to them that the real thing that's a problem in climate change is spring. Because if you raise the temperature 1 Celsius, but if you have a huge change in temperature. So I looked at when did we have these temperatures. This is going back. Ones in red there are for the maximum temperature. The interesting thing is if you look at the extremes, high temperature, one. And if you look at the minimum temperatures, there's only one. That was so most of our extreme temperatures haven't been important. Look at other locations. The thing we're worried about is what are these extremes? Are the extremes going to get worse? Do we have a shift one way or the other, and how much is the probability of extreme events increasing or decreasing, or what's happening? Okay, so I keep mentioning probability and risk. This is the thing the farmer really needs to know. I've worked on this on frost protection a lot. Give people ideas on how they should plan. How often do they expect to have frost events? What kind of economic impact does that have? We can say the same thing about high temperatures, floods, and so on. It gives them a probability and a risk that they can deal with. And well, I'm willing to take this chance that I'm not going to have a frost. So maybe they need to put away some money for that 1 year when it's crazy. Okay, probability is the chance that some extreme event might occur in any given year. So like if I said it was a 1% probability of a flood, that would be 100 floods. 1 year out of 100 flood. Well, that could happen, 2 or 3 years in a row. It might not happen for 30 years. All kinds of the probability in any given year may be 1%. Probability it happens or the risk that it will happen within 5 years or 10 years is different. It's the same thing that we use for earthquakes. At the probability. So I put this little figure on here to give you an idea of what's going on. If you look at the probability on the bottom, this is the probability that something might happen in 1 year. So I have 1%. On the y-axis there, you can see it goes 0. That's the risk that something will happen in a certain number of years. The red line is for 5 years, yellow for 10, that blue line is 10 top line. So if I have a 100-year flood, for example, if I look at the 1% probability, the risk that that's going to happen, I don't have a pointer. I look at this probability. If I go up to this red line here, the risk that that will happen is about less than 10%. So in 5 years, that's the risk that that'll happen 1 or more times is much more than 1%. If I go for 30 years, if I go up to that top line, it's like it's almost up to 30%. That's the same thing you get with earthquakes. If you have an earthquake 1 year out of 100, if you go over time, you went back 1,000 years, you got one every 100 years, that'd be a 1% probability. The risk that that will happen within the next 30 years could be up close to 30%. Because it either happens or it doesn't happen in a given year. So binomial distribution. Earthquake will happen, flood will happen. So you can use this also for agriculture to look at what's going to happen. How do the farmers adapt? How do they plan? Well, I'm going to show you some of the probability density functions for different parameters. This is for June through August, and it's showing the extreme high temperatures. I took the high temperatures recorded in different periods, 1951 to 69, 70 to 1966. I broke it into 3 periods. Then I drew the probability density function for the high temperatures in those different periods. Just to see how things And the yellow line, the yellow curve there, is the one for 2006. And that's the most recent. Look at that. It's higher in the middle and it's lower out there. But if you're looking at extreme high temperatures, say more than 110 degrees, the probability has decreased. Less likely that recent times we've had less probability of having a bigger probability and more likely to happen. So if anything, well, maybe the means are going up, but the extremes haven't. So that's, again, this is based on the Napa data. It may be different somewhere else. Generally, I find similar. Means, you can see, this is the mean of the extreme high temperatures. They haven't really changed it. Probability has, and it's less probable to have the extreme high temperatures now than it has in the past. Now, there may be other factors involved in that. Napa State Hospital has grass around it. It probably didn't irrigate as much in the past. They probably irrigate more. There's other things that can affect the climate data too. We're assuming that there hasn't been any big change. Okay, now this is Napa State Hospital again. This is showing the extreme low temperature. Showing from, again, the same periods again. The yellow line is 2006. See, if you look at these probability density functions, that it's shifted more to the right. So we're less likely to have frost than we did in the past. It's changed a lot. It's actually changed a lot. Look here, 30 degrees, that's a very low probability that they're going to have a frost up in Napa Valley based on data from the actually which fits with what we've been observing. The minimum temperature. So this is good in terms of climate change. This is related to climate change. This is weather change, okay, because it's only in the last years. Climate change, the pattern continues, maybe. Okay. This is the annual maximum rainfall event, and broken down by the same time period. You can see that the means haven't changed very much. But if you look at that red line, that was back 1970 to 1988. Look at that red line. The probability of having an extreme rainfall event was pretty high during that. Something was going on with the weather. A lot bigger risk of having a flood back then. Now it's similar to what it was back. So if something's going on, it looks like there's something specific causing not climate change. It's too fast. 1 year. There's something mixed in with the climate. And I put this on here. This was just to show the growers, because they were concerned about what happened in September. They lost the hot, dry wind that occurred in 2004. So I looked at the reference evapotranspiration. I'm going to explain that later on. And I looked at, that's what we use as a measure of evapotranspiration. And so the yellow one here is for July. Dash line here. Reddish one is for August. 2 lines. So the evapotranspiration rates in September are pretty low. Probability of having a real high value is still not that great. Because, let me give you an example. Anybody here have an idea? What's the typical evapotranspiration rate in Central State Sacramento data set? Anybody have an idea? How many people from DWR do we have? We got one. Take a wild guess. How many inches a day do you think is typical? Quarter of an inch a day. It's about 2,500. So you can see that in September, up in Napa, they have a fairly good probability they might get above that, but it's not going to get much higher than that. So these are extreme high events. This is the extreme value. Okay, so the conclusions from Napa: probability of extreme events is more important than increasing. I think there's no doubt about that. The big thing you're worried about was climate change and agriculture. Risk of extreme events is higher than the probability. So if you're looking at the risk over a certain period of time, the risk is higher than the probability in any given year. The risk of extreme high temperatures, June through August, decreased after Napa. And again, I see that in other places too. Risk of extreme low temperatures has lessened. There's not as much frost as there used to be. And the risk of extreme rainfall events has decreased after. Okay, so what about, let's go on to some other things, because we have a lot to talk about. Like I said, there's 230 crops, and we've only done wine grapes. We're on a roll here. What about the climate change effects on fruits and nuts? Talk to the pomologists in Davis. They're going to tell you that they're worried about this. It does have an effect on killing and heat. Okay, they haven't gotten too much into heat stress, but other than prunes. They're talking about problems with prunes because of heat stress. But there's a problem with killing. Okay, I got some of this information from Ted Young, who's a professor of ecology. One of the things is floral initiation differentiation occurs in the summer and fall prior to bloom. So if you have really strange changes in the weather during the summer and the fall, you can affect what happens. You know that already. High heat or water stress during the summer and early fall can cause fruit defects. You can get bad fruit. Bad fruit doesn't sell as much. Sell the fruit that is quality. Cause all kinds of defects, double fruit, have abnormalities next year, even if you have stress during the summer. And increased summer heat and or limited water availability in the fall can affect fruit quality. Several percent. Okay, so water has a big effect. That's controlled a lot by irrigation. So if you have the irrigation volume, control that. Flowering and fruit set, flowering date and characteristics of bloom are strongly affected by winter chilling and post-rest heating. So winter chilling is if you get temperatures between about 7 degrees Celsius and about 0. You have to get so many hours in that range in order to get some plants to bloom. Some crops, there's big differences in the process for how many hours they need in that chilling. Some of them require quite a few hours. Start getting warm and you don't get as cold a temperature. What that means is they're going to have to change varieties. It depends on how fast that occurs. If you have climate change that warms up, you don't get the chilling. Winter chilling in the Central Valley is strongly affected by fog layer. We mentioned earlier, I mentioned fog is changing. I haven't seen it very clear to me. I remember not being able to see it on my face. It hasn't happened for a long time. Decreased winter chilling results in staggered bloom, bad pollination, reduced fruit set, poor fruit quality. Apricots and cherries can drop their flower buds at a crop in low chill years. I've run into growers who, on the coast, sometimes they don't get enough chilling. So that could expand and get more of that. This global warming comes down to the region scale. Fruit set of prunes is regularly affected by high temperatures, dry winds, and bloom. I was talking to the prune working group weeks ago, and they 2,000 prunes and they lost the whole crop. The whole crop was lost because they had some hot, dry winds during bloom. Never happened before. I figured out the probability was 5 standard deviations above the mean. Probability that this would happen. So I don't think it's going to happen again in the near future. But that was a really extreme. So they're looking into that. They're trying to study that to see how important it is to do that. Bad weather during bloom and harvest can also have problems. Bees don't pollinate well when it's raining. Almond growers are very aware of this. Raining, the bees don't go out and pollinate. They don't pollinate the walnut. Flower, you don't get into that. So they really worry about bee pollination. Rain near or during harvest increases the incidence of fruit ground rot and other fruit and nut diseases. Rain near harvest can cause fruit cracking, destroy the crop, or late spring and summer rains can have an effect on tree fruit and nut quality, production. Okay, now I'm going to talk about evapotranspiration because this is something I get asked all the time. And people want to know, is climate change going to increase evapotranspiration because the temperatures are going up? That means we need more water for growing crops in California. So I'm going to talk about how crop yield is estimated. Actually, No big deal. Can talk. So I'm going to talk about how crop evapotranspiration is estimated. I've come to several of these seminars. So far, I haven't seen any equations. And I'm the extension specialist. So the number one rule they tell you when you're an extension specialist, never put up an equation. So I'm going to do it. And what variables affect ET is really important to understand. And climate change is how climate change affects evapotranspiration. How am I doing? A little quiet? You can talk to these guys? Okay. Okay, this is kind of a little diagram to show you how we estimate evapotranspiration in California. Basically, we use reference evapotranspiration, ETO. And what that is, it's an estimate of the evapotranspiration of an irrigated pasture water stress. So that's the standard. It's used all over the world, except for a few states in the northwestern United States. So everywhere else they use. What we do is we take that number, we multiply by a crop coefficient, and adjust from that reference ET, from the irrigated pasture, to different crops. So if you want to go from an irrigated pasture to a citrus orchard, then you have to make a correction, because it depends on how frequently irrigate, how big it is, and other things I can't get into today. But anyway, there are correction factors for different crops. And then the last thing is if you have water stress for some reason, then you have to make a correction for the effect of water stress on it. Okay, so most of the time in California, we don't have that much water stress. The farmers doing a good job. Usually we only do the first two. Okay, this is some data that I took from Meadowland. Anybody know where, well, I said where, it's near El Centro. Okay, Meadowland is the university research station. And I plotted up there ETO, reference ET, versus mean temperature. And you can see there's clearly a relationship between ETO, reference ET, and temperature. So the logical thing, if you saw that, if you were reading a newspaper and you saw this graph, and you'd say, oh, well, there's a good relationship between temperature and evapotranspiration. If the temperature goes up, I think the ETO is going to go up. So the logical thing is you'd say, well, with climate change, we expect to have more ETO. Now, we already talked before. It's pretty common to have 35 degrees Celsius, Sacramento. If we go up to 40 degrees Celsius, if I extend that up there, if you look at the evapotranspiration rate, it's about 9.5 millimeters a day. Okay. Anybody know what the average? No, I told you it's 2,500. So all you have to do is be able to convert between inches and millimeters. But if you have 2,500ths of an inch per day of evapotranspiration, what is that in millimeters? No, between 6 and 7 millimeters a day. We get 40 degrees here quite often, but we don't get 9.5 millimeters. So right off the bat, this should tell you that temperature and ETO are not necessarily directly related. There's a correlation between ETO, between reference ET and temperature, but they're not the same. It's not a deterministic thing. It's not a dependent variable and independent variable. Other factors involved. That's one of the problems you run into with climate change. And people say, oh, well, the temperature is going up, so we're going to have higher ET. Not necessarily the case. There's another example. This is also Meadowland data. Out of this data, again, the ETO rate, millimeters a day versus the temperature. Here, there's no relationship at all. The difference is this is daily data from July. This is daily data from July, and this was monthly mean data. Okay, so if you do monthly means, you'll find a relationship because it's cold in the winter and the ET is low in the winter, and it's warm in the summer and the ET is high in the summer. So you'll get that in if you do it annually. But if you look at it on a monthly basis, you won't get that. Because day to day, there's not that much relationship between temperature. So using ET and the fact that temperature is increasing to say ET is going to increase is not necessarily true. It is a factor. It does have an impact, and I'll show you how it's related. California, we have the CIMIS network. We have a network of weather stations, California Irrigation Management Information System, somewhere between 120 and 130 stations. Nobody knows. They keep changing all the time. But they're all located over irrigated grass, and we use a standard equation to estimate ETO. This was done back in the 80s. It's been used a lot for water conservation. I put it up here because I want to show you the things that are important. You have to measure For the pyronometer, you have to measure solar radiation because that's the main source of energy. You have to measure the air temperature. It does have an effect on evapotranspiration. You have to know the humidity because it has an effect on evapotranspiration. You have to know the wind speed. So there are 4 things that determine the evapotranspiration. The main one is the radiation. Solar radiation is the main factor that affects evapotranspiration. Again, if you look, the solar radiation is low in the winter and high in the summer, so the ETO is low in the winter and summer. This happens that temperature is also correlated with radiation. That's why you get that correlation with temperature. So the main thing is the solar radiation. Secondarily, I would say it's probably wind speed. If you're in a windy place, you're going to have higher ET. Okay, here's the equation. And I simplified it. You don't get the full equation. You only get part of it. And so I simplified it a lot, actually. But LE, I use for, it's a latent heat of evaporation, or latent energy of evaporation, okay? It's the latent heat of evaporation multiplied by the mass flux of water vapor. And so LE is evapotranspiration. You can calculate the evapotranspiration using energy because it takes energy to break hydrogen bonds and send water molecules off. That's what's going on. The more energy you have, the more water molecules you can break off and send off into the air. You can express it in this way. There's W1 is a weighting function. I'm going to explain that in a bit, multiplied by the net radiation. So that's the amount of energy, radiant energy, that gets absorbed and actually absorbed at the surface. So you have to subtract off what's reflected back off, and you have to take into account the long-wave radiation that I won't go into, but the biggest factor that affects the difference between plants, I think the biggest factor is the difference in albedo, how much radiation is reflected away from it. The second term over here, that first term is called the available energy because that's the source of the energy for the evapotranspiration and for heating the air. The second term is to take into account how much energy is coming from the air that's being supplied for evapotranspiration. This is where the temperature has an effect. The W2, again, is a weighting factor. And again, I'll explain the weighting factor in a second. And the ES minus E, that's the saturation vapor pressure minus the actual vapor pressure, and divided by RA. RA is the resistance, aerodynamic resistance to heat transfer. And that really depends on, the R sub A depends on how turbulent the air is. And the turbulence depends on how fast the wind blows and how rough the surface is. If you have a rough surface, you have more turbulence. If the wind blows faster, you have more turbulence. Okay, so that, what that does, it has an effect on how readily heat is transferred down to the plant to supply extra energy for evaporating water. The vapor pressure difference, actually what that term does, it tells you the difference between the air temperature and the plant. And the resistance tells you how readily that energy gets transferred. But it takes about another hour or 2 to explain that all to you, so I'm not going to do that. But that's the sensible energy source for evapotranspiration. Those weighting functions you see down here at the bottom, the W1 is delta over delta plus gamma times 1 plus RC over RA. W2 is this one here, it's rho Cp, it's a volumetric heat capacity. How much energy do you have to add to raise the temperature of this volume of air 1 degree Celsius? And the bottom we have the delta plus gamma, then times this 1 plus RC over RA. Where these things come in, the delta, what that is, that's a measure of, that's the slope of the saturation vapor pressure curve. It depends on the temperature. Okay, so the temperature affects delta. The gamma is a constant. This R sub C is the canopy resistance. That's the resistance for water coming out of the plant going to the atmosphere. So it's affected by the stomata and how wet the soil is. That affects this R sub C. And R sub A, we already said, was the aerodynamic resistance. It has to do with the turbulence over there. Okay, well, the temperature affects the delta. The gamma is a constant. RC depends on the canopy resistance, so it depends on the plant stomata mainly. This depends on how rough the surface is. The Rn depends on solar radiation. And E sub S depends on the temperature. So these things, it depends on those 4 things that I mentioned before, the radiation, the temperature, the humidity, and the wind speed. But they interact in funny ways. Okay, it's not a simple thing. It's not one parameter that affects it all the same. So I'm going to look at what's going to happen. And I took this from Roderick and Farquhar, 2002. It's an article in Science. And what they did was they were looking at evaporation pans and why evaporation pans have been decreasing. evaporation from pans has been decreasing. They found this in Russia and they found it in China. And so everybody said, well, if the evaporation rate's going down for pans, then that must be we must be having cooling and not warming. Well, then people started writing all kinds of articles about why that's wrong. And there's all kinds of people who've been arguing about this for about the last 2 or 3 years. But anyway, in their article, they said in the last 50 years, the change in the mean temperature has gone up about 0.15 degrees Celsius per decade. That's kind of the average global change. Change in the maximum temperature has been about 0.1 degrees Celsius per decade. Change in the minimum is about 0.2. So you can see it's about twice as much as the maximum, twice the rate. And the change in ES minus E, that's the vapor pressure deficit. Saturation vapor pressure minus actual vapor pressure hasn't changed. This E sub S is a function of the temperature. It's an exponential function of temperature. So temperature is going up, so that means E sub S is going up. E, that E is the vapor pressure. That's the humidity. So it's got to be going up too. The humidity has to be increasing for this to stay the same. It has to be. Okay? So if you take this information and we look at, well, what's happening through the evapotranspiration? Okay, I mentioned they did this for evaporation pans. For you, those of you who haven't seen an evaporation pan, this is the pan at the West Side Field Station. DWR operates this pan. And what it does is you fill it with water and they just measure the evaporation every day and they record this stuff and they use that as a measure of the evaporation rate. And what happened was in China and Russia, they were observing that the evaporation rates have been decreasing, which seemed counterintuitive because temperature is going up. So they would have thought, well, it should go up. So people were trying to explain why this is. And there's all kinds of things about, well, the area is having more evaporation, so there's more humidity, and that causes the panic. Other people talk about, you could argue and say more birds are drinking the water, things like that. Because that is a problem, actually. But what it ends up is that the temperature has a very little effect on evaporation. Radiation is the main thing. As the radiation goes into the water, it gets absorbed by the water, it has a very high net radiation. It captures a lot of that radiation, warms the water up, and that's what becomes radiation. Because it's a nice smooth surface, when the air blows over it, there's not a lot of transfer of heat from the air. The temperature is not a big factor. Okay? And the reason why it's going down, they think, is because of global dimming, because of air pollution. Air pollution has increased, and that they think that's reduced the radiation, and that's what caused the pan evaporation. So, but people argue about that. That's my opinion. I think that's what it is. So evaporation pan depends on radiation, temperature, wind speed, and dew point. And global dimming, I think, is probably what caused the evaporation to go down. Okay, I mentioned before about stomata. This is an example of stomata from beans, common beans. And the one on the left has an open stomata. The one on the right is closed. Stomata partially closed to maintain a fixed CO2. I'm not going to go into the physiology a lot, but they try to keep the CO2 concentration inside the stomata. The plants try to maintain the same concentration all the time. And so if there's too much CO2 in there, they partially close the stomata to try to control that. Well, if you close the stomata, that's also where the water vapor comes out and you have transpiration. So you can affect transpiration when you close to try to keep the CO2 out. Okay, so this can reduce transpiration. It also increases leaf temperatures, and sometimes you don't get a reduced transpiration. You may partially close the stomata and it doesn't affect transpiration. You raise the temperature, because then you have more energy to vaporize water and you have more water vapor going out to a smaller opening. But if you close it enough, then you will start to reduce it. So currently, if you use the current conditions, 360 parts per million CO2, if you calculate the canopy resistance, this is what we did when we used the reference ET equation. It comes out it's about 70 seconds per meter. If I have more time to explain more about this, but it's a measure of the resistance to water vapor coming out of all the leaves. Okay, and that's based on current CO2 conditions. If they raise the CO2 up to 550 parts per million, then based on the FACE studies, I used the FACE studies that were done where they use CO2 enhancement, we estimated that it should be about 0.85 seconds per meter if you went up to 550 parts per million. So that means that there's more resistance. The stomata will partially close because of the higher CO2 concentration in the atmosphere, which should reduce evapotranspiration a little bit. Okay, so now let's go through a little scenario and we'll look at what might happen. This is the possible temperature increases you might expect. The green line shows the mean temperature, the blue line the maximum, the red minimum. What I did was I had this go from increasing 6 degrees, and if you look at the green line, it starts at 22, it ends up to 20. But the maximum was increasing, or the minimum was increasing twice as fast as the maximum. So I did it on purpose that way, so it follows pretty much what's been happening. And this is what you might expect out to the year 2100, for example. So if I look at the saturation vapor pressure for that change, and I look at the vapor pressure, assuming that the dew point goes up the same as the minimum temperature, PPD doesn't change. The ES minus E doesn't change. So it's exactly what they've been observing. Okay? It's exactly the same as what they've been observing. Saturation vapor pressure is going up because the temperature is going up, but the vapor pressure is also going up, the E, because we're adding more water vapor to the air. Okay? So the next thing, well, what happens to this weighting function, that W2 that we have? And the W2, again, shows up here in this little box. The weighting factor, if I change, the blue line shows for 550 parts per million, with a canopy resistance of 85 seconds per meter, and the red line shows for 360 parts per million. So you can see that that W2 is a little bit lower if you have higher CO2 concentration, but both of them drop. As you increase the temperature, that W2 gets smaller. Okay, well, the ES minus E didn't change. ES minus E didn't change at all, but the W2 is getting smaller. So if you have temperature increase, that means this term right here, the central energy term, is going to decrease. So you increase temperature, that part of the equation is going to decrease. ES minus E doesn't change, W2 gets smaller. So what happens to the available term, the W1 times Rn, okay, the net radiation? Well, the available term could change if you have cloudiness. If you have more clouds, it will affect it because you'd affect the radiation. If you change the air turbidity, air pollution can affect it. Cloudiness, all kinds of things can affect that radiation down. But what about the W1? What ends up, the W1 increases with temperature because that delta that I talked about before, the delta is increasing with temperature. So if you put in some numbers for the delta over delta plus gamma times that, you'll see that that W1 will increase the temperature. But it makes a difference whether you have 550 parts per million, the blue line, or the red line with 360 parts per million. So if you increase the CO2, then the effect is less than if you don't increase the CO2. So if we start right there, up there at 7, 8, red line, so that would be at 360 parts per million. If we're increasing to 550 parts per million, we could go out to 4 degrees or so, and we haven't changed anything. It's still the same. The W1 hasn't changed. So if we start going higher than 4 degrees Celsius, then you might start to see an increase in the W1. But if that happens, it also depends on whether or not this comes true. Because this 85 seconds per meter, nobody's ever measured that. So we guessed at it from stomata resistance measurement base study. Okay? So I'm going to put this all together, and we'll look at some different possibilities of what might happen. This is over a year showing what the cumulative ETO might be. This would be, again, for an irrigated pasture. And I had several different things up there. The top one is showing if I have an increase in maximum temperature of 2 degrees and the minimum dew point doesn't change, I increase the canopy resistance 5 seconds per meter. Okay, that's that top line up there. That's the one that would have the highest evapotranspiration. The blue line is the current condition. The blue line is right here in the middle. That's the one where you have no change in the maximum temperature, no change in the minimum temperature, no change in the dew point, and the canopy resistance is 70 seconds per meter. If I only change the canopy resistance, if I increase the maximum temperature by 2 degrees, the minimum by 4 degrees, the dew point by 4 degrees, so the same as the minimum, the canopy resistance, I keep it 70 seconds per meter. That's the red line. So the ET, the evapotranspiration, would increase a little bit. It would increase a little bit. That's assuming that the canopy resistance doesn't change. But if I increase the canopy resistance, like make it 85 seconds, then it actually decreases. So there's a possibility that we could actually have a decrease in evapotranspiration with temperature rise up to a certain point. Now, if you start getting more than 4 or 5 degrees Celsius, then all bets are off. It might start going up more. But up to that point, I don't see a big serious problem. Okay? Getting on time. Ooh, don't have much time. Okay, let me, that was the main point I wanted to make. I want to show you this about precipitation, then we'll stop. Okay, this is a graph from Fritz, 1984, and this shows the precipitation pattern. If any of you guys remember your history book, this is the Donner Party. They were really unlucky because if you look at that, they had a lot of drought after that 1 year. So that was about as unlucky as you could possibly get. But anyway, the thing I wanted you to notice, this goes up to 1984. And the first thing that strikes me when I look at this graph is there was a lot of drought, a lot of low rainfall in the past. This 24, this is about 24 inches per year. That's the average. Corresponds to the 1901 to 1961 mean value. Well, if I looked at that graph, even if I was a little kid, the first thing I'd say is, well, we need to lower that mean down. Okay, because why should we base it on this period? Here, maybe that mean should be lower. That's the first thing I would do. But what it tells me is there's a lot of potential for drought. I don't know what caused that drought in the past. I have no idea what caused it. I don't know if anybody's ever said what caused the drought. But it has happened in the past, and it's probably going to happen again. In fact, if you go back beyond this, it's even been worse. So I do think that it's a problem. Drought is probably a bigger problem than the ET. Okay, because if you don't have the water, you have to do something. One of the things, this is what happens when you have a drought. The on-farm efficiency improves, you improve the application efficiency, the scheduling, the system. Whenever you have a drought, the farmers are a lot more efficient because they're really concerned about it. They go out and they work at it. And usually what happens is they have less irrigated crop acreage, so they quit planting as much crop. The field crops, they take them out. They do more groundwater pumping, more water transfer. So people don't, you take rice out of production, you can sell your water to somebody else. If you take a corn crop and you don't want to produce the corn, you can sell your water to somebody else. What's happening in California, I don't know if you've driven down I-5 and you notice all the trees down there. When I was there, when I came to California 27 years ago, there weren't any trees then. Not till you got way down the valley. So now there's a lot of permanent crops, and those crops are going to need water even if you have a drought. So they're going to be paying top dollar to get water from the field crop growers. But you have to have the flexibility to move that water around. And then you also have the problem of, well, what happens? This is what happened in Australia. It has a big drought. I don't know if you've been keeping up on this or not, but there's a shortage of rice around the world. And that shortage of rice is because of the drought in Australia. So the Australian rice farmers are selling water to the wine grape growers. They're producing wine grapes, but now there's a shortage of rice. And so it's caused all kinds of hoarding in Hong Kong, the Philippines. They've had violent protests in a lot of different countries. So it has an impact outside of the local area. The same thing would happen in California. It's not going to destroy California's economy because it's not mostly agriculture. That's the other thing. But it will have a big impact. It'll have an impact on locally, on the farmers and the local communities, but it also affects people outside of California. So we do need to be concerned about it. I'm going to stop there because I'm going too long. I need 4 or 5 more hours. So sorry about that. Okay. Any questions? Yep. That's a good question. I honestly don't know. The question was about when they stopped doing the rice burning in the Sacramento Valley, whether or not the less pollution from the rice fields, rice burning has caused an increase in radiation and hence evapotranspiration. I don't know. That's something that'd be interesting. We could go back and look at that. I think we have the data. We could probably check that out. Right offhand, I don't know. But that's a good question. Yes. Nitrogen in the air or in the soil? You mean CO2 or? Because nitrogen, it's mostly nitrogen. Well, water vapor. One of the things I worry about is that water vapor is also is a better greenhouse gas than CO2. So if you start putting more water vapor in the air, you have positive feedback. It's going to make it even worse. You know, like the ice, the glaciers melting and stuff. Part of that's because there's more total energy, more enthalpy in the atmosphere, because you're putting not only raising the temperature, you're also putting more water vapor in there. That raises the total energy content. That's part of the reason I think why those the ice shields, glaciers and stuff are melting faster than the water vapor in addition to the temperature. I always ask this question of my students in class. I always ask them if you have to buy an ice cream cone for your boyfriend or girlfriend, is it better to buy an ice cream cone in a place with 80% relative humidity or with 20% relative? Which place is it going to melt faster? Well, actually, it's going to evaporate faster where you have 20%, but it's going to melt faster where you have 80% left if you have the same temperature because there's more heat in it. Okay, that's one of the things why humidity is important. Who's the next person in the back? You know, I don't know the numbers on rice, but I know I have a big problem this year because I'm supposed to do research on fallow rice fields and I can't find any. They're planting every field this year because of this rice shortage because the prices are just skyrocketing. So every rice farmer in California, we're taking advantage of the world market right now. I don't know about the varieties, but rice prices are still way up, and so all the rice is being planted. No, probably not. I don't know the variety difference. Yeah, yeah. I know that it's a problem for me because, like I said, we've been trying to find a fallow rice field. Not this year. California could do what to itself? No, I think you know California was at the it's like 25% of the agricultural production in the United States is from California, and you know you might reduce it down for sure. It could maybe go down 20, 15% production in the United States. But we produce high value crops more than other states. We have oranges and we have grapes and table grapes and they're not the staples. It's not wheat and but we produce wheat and maize and other things too. But I don't think it's not a point of problem of us not being able to feed ourselves. Problem of what impact will this have if we have reduced production on the rest of the United States and the rest of the world? It could have an impact. If we had a serious drought like the one that I showed you, that was like 30 or well 40 or 50 years long, then yeah, we'd have a big problem. I don't. It's not a matter of us feeding ourselves. We have money. We could buy food from other places. Because the agriculture is not the main industry in California. It is an important industry, but it's not the main. Yeah. Pesticide correlation. If I had more time, I would have talked more about pest problems, pest management problems. But I don't know anything about. You said pesticides or pests? Pests. Okay. The question was about. See if I paraphrase this right. I'm not sure if I do or not. But whether or not the maximum temperatures have been related to pests, insects and diseases coming in. There is some information. One of the things I was going to talk about was the citrus problems. They have citrus canker. I think they've related to, in Florida, for example, they've related to the hurricanes. For sure, the hurricanes have caused the introduction of citrus canker coming from Cuba. They don't know if it's from Cuba or from Brazil, but it came in with hurricane. It has to do with the damage caused when the tree trunks and stuff are hit by, hit by debris, and it infects the plants. And so citrus canker was introduced by hurricanes, which they think possibly related to climate change. So I've heard things like that. I haven't heard anything about maximum temperature alone. But climate change in general, maybe. I mean, if you have more rainfall, you have more disease problems. Some cases, I was going to give you some examples where higher temperatures actually help with some pests. Red scale is a little better if you have some high temperatures. So there are some things are worse, some things are better. But as far as introducing new pests, I don't know.